Now, these three examples are in your notes packet. Unfortunately, they're the only three that go along with this section. And so you can do these three, but then again, you'll probably want to add some extra paper behind it to give you some more support and more things to look at. So we have, if f of x is not a rational function and you wish to find the limit as x approaches infinity or as x approaches negative infinity, it says use common sense. But I don't like that word common sense. Let's mark that out. And instead of common sense, we're going to use critical thinking. Because if you see the word common sense, that gives us the impression that the problems are going to be easy or they should be easy. But if you can't figure them out, that might make us not feel very smart. And so I don't think that's a good word choice. So let's change it to critical thinking. Okay, so then we're going to attempt to see whether the numerator is growing faster than the denominator using those three cases I mentioned earlier in the previous video. Or if that doesn't work, so that's one option. The second option, if that doesn't work, is to plug in large or small numbers to confirm your theory. And we'll see when each would be appropriate as we go along. But we always want to try to identify or ID the most dominant terms in the numerator and denominator, because those can be a huge hint to us as we're working out these problems. So on 8a, I see that there is an x over e to the x. Well, there's only one term in the numerator and only one term in the denominator. E to the x is exponential, so e to the x is growing faster. The denominator is growing faster. So since the denominator is growing faster and we're approaching positive infinity, we'll say that our limit is equal to 0. The second one, I need to identify the most dominant terms. So the most dominant term in the numerator is e to the x. Most dominant term in the denominator is also e to the x. So I look at the ratio of the leading coefficients there. So that would be 1 over 1. And 1 divided by 1 is 1. Now this third example, the limit as x approaches infinity of sine of x over x. Ooh, Miss Honeycutt didn't talk about sine. But you have had sine in your past. Remember, sine is that nice periodic function that goes up and down and up and down. Well, as the x values get larger, the highest sine will ever be is positive 1. And the lowest sine will ever be is negative 1. So I can't figure out if the top is going to grow faster than the bottom because sine keeps going back and forth, back and forth, back and forth. But I can think about some reasoning here because sine, the top, is always going to oscillate back and forth between negative 1 to positive 1. So the numerator is only ever going to be a number between positive 1 and negative 1. Yes, it will go back and forth, but it's only going to be in between those two numbers. Now, x, the denominator, is going to keep growing. So that's going to be a really, really big number. So if I take numbers from negative 1 to 1, and I continue to divide those by bigger and bigger and bigger and bigger numbers, then I'll only end up with something like a positive 1 divided by 1,000,000 or negative 1 divided by 1,000,000. And essentially, that is always going to be 0. So I can say that this is going to be 0. If I take negative 1 divided by a big number, I get 0. Positive 1 divided by a big number, I get 0. So anything in between there would also divide by a big number and get 0. By the way, that informally is what's called the squeeze theorem. I'm not going to test you on that, but if you ever go to another calculus class and they mention the squeeze theorem, that's what it is. Okay, now, unfortunately, those are the only examples, but there's so much more to explore. So I took some examples from Delta Math. I'm going to use these, add them into your notes, and we'll look at what we have here. So the second example, or not second, whatever example this is, we're looking at the limit as x approaches infinity of 2e to the x. So it's not a rational function, so it wouldn't make sense for me to think about is the numerator or denominator growing faster because there's no fraction here, it's just one term. So instead, I'm going to think about x being a big number. So I'm going to think about 2e, and instead of the x, I'm just going to write the word big. And I'll think about what's happening there. Okay, so 2 times e to a really big number. Well, e to a really big number is big, and 2 times that big number is really, really big. You like that? It sounds so mathy, right? Really, really big. Really big. It's going to feel like you're cheating math and just doing math as big and little, but that's really how I want you to think about this section when you're exploring dominance. So we'll say the limit as x approaches infinity of 2e to the x is actually infinity. Now, bonus, I'm going to make up a new problem that's not already printed on here. Instead, let's take the limit as x approaches negative infinity of 2e to the x. So this time I'm thinking about substituting in values for x that are approaching negative infinity. So 2e to a negative. I'm going to say negative big because I want you to think of like a million, but it's negative a million. And also let's think about like properties of exponents. Because if you have a negative exponent, what that does is it sends whatever has the negative exponent to the denominator and makes it positive. So now I have 2 over e to the big number, to a big number, which is really like 2 over something that's really big. I'm giggling because really big sounds not very intelligent, but really big is how we say that, or how we're going to think about it. So 2 divided by a really big number, is pretty much 0. So the limit as x approaches negative infinity of 2e to the x is 0. Now, the more you do these, the better you'll feel about them. So let's just go through some more examples here. All right, here now we have rational functions, and I want to compare with the dominant term. So first of all, I'm going to identify the dominant terms. If I can get my highlighter. Okay, so the most dominant term in the numerator is the square root of 4x squared. The most dominant term in the denominator is negative 5x. Now the problem does ask me to approach negative infinity, and I will, but I'm going to do a different problem first because I think it will be easier to do positive infinity first. So first, I'm going to do the limit as x approaches positive infinity of the square root of 4x squared minus 4x over 5 minus 5x. Now, keep in mind, I'm making up this problem. So this is like I'm adding an extra example. So like ignore this one for a minute. Let's work on this problem, and then we'll try to approach negative infinity and on the other side. Okay, so again, my most dominant terms right there. I want to compare the limit of the most dominant terms. That's all I have to compare. So the limit as x approaches infinity, the square of the square root of 4x squared divided by negative 5x. Now I can simplify the square root of 4x squared to be 2x over negative 5x. And hey, look, those degrees are the same of the numerator and denominator. So just look at the ratio of the leading coefficients, and I get 2/5 or negative 2/5. So I'll say that this limit as x approaches infinity of that entire function is negative 2/5. Now you do have to be careful though when x approaches negative infinity. So let's go back over to this other side and think about it when x approaches negative infinity. So for real, we're doing the problem now. So I'm going to again compare the most dominant terms. So the limit as x approaches negative infinity of the square root of 4x squared over negative 5x. And I can simplify the square root of 4x squared to be 2x over negative 5x. And again, it looks like I'm going to have negative 2/5 if you compare, but keep in mind we're approaching negative infinity, so the numbers that you're going to be substituting in for x are going to be negative. Except in the numerator, right here, this 2x is going to be squared. So whatever is up in the numerator is always going to be positive, no matter what. So when I evaluate this, I'm going to say, okay, that 2 is always positive because it ends up being squared earlier, and then also it was squared here, and you take the square root of it, and we can't take the square root of a negative number, otherwise we get something that doesn't exist. So that numerator is going to stay positive. The denominator, though, is like we're going to have a negative 5 times a negative, and then negative 5 times negative blah blah is positive 2/5. So this is equal to 2/5. Okay, let's see, what else can we do? Let's move down to, you'll have a few that are radical. Sometimes they approach positive infinity. Sometimes they approach negative infinity. So be careful with that. Watch out for what it asks you for. And then you'll have some that involve the e's. So let's look to see what happens if there's an e involved in my problem. We still want to compare and identify the most dominant terms in the numerator and the denominator. So in the numerator, it looks like the most dominant term is e to the x. And in the denominator, 6x cubed. And as long as we're approaching positive values, e to the x is a really big number. 6x cubed is another big number. Since the numerator is growing faster, then that implies my limit is going to be equal to either positive infinity or negative infinity, and I have to determine the sign. So let's compare the limit as x approaches infinity of e to the x over 6x cubed. So I'm going to think about substituting in really big numbers for x since we are approaching infinity. And I only have to figure out if I need a positive infinity or negative infinity. Well, e to a really big number is positive. Oh, I should have written big here. E times a big number cubed is also positive, and a positive divided by a positive is positive. So I'll say that this limit as x approaches infinity of x cubed plus e to the x over 6x cubed plus 4 to the x is positive infinity. But what if instead of approaching positive infinity, that limit approaches negative infinity? So let's rewrite that problem. X cubed plus e to the x over 6x cubed plus 4x. And I go to identify my most dominant terms. And it looks like you got to be careful with this e to the x when you're approaching negative infinity. Because it looks like e to the x would be a most dominant term. But think about this. E to the x, substituting in values for towards negative infinity, would be a negative really big number. So e to the negative big, because that's a negative exponent, that's the same as 1 over e to a really big number. And 1 divided by e to a big number is 1 over a really big number. And 1 divided by a really big number is pretty much 0. So when x approaches negative infinity, e to the x approaches 0. I should use a different color. E to the x approaches 0. And so that means it's no longer the dominant term. So that's going to happen when x approaches negative infinity. So e to the x is not the dominant term. This time, the dominant term is x cubed on top. And then the denominator, 6x cubed. Oh, look, the degrees are the same. So I just evaluate the ratio of the leading coefficient. The leading coefficient of the top is 1. The leading coefficient of the bottom is 6, and I'm just double checking. If I have 1 times a negative big number cubed over 6 times a negative big number cubed, I'm going to get 1/6, but I want to double check my signs. A negative big cubed is a negative. Negative big cubed is also a negative, and negative divided by negative is positive 1/6. So I would say this limit equals positive 1/6. Here we have another one where we have one of those instances with an e term in there. So this time we're going to determine whether the following limit is equal to infinity, negative infinity, or some specific value. And this time x is approaching positive infinity. So it's not a rational function. So I'm going to think of this as, first of all, I want to look at my most dominant term. It looks like the most dominant term here is e to the negative x. So I'm going to think about e to the negative x, but I'm going to substitute in really large values for x. So like e to the negative big. But again, a negative exponent means that you take that term and put it in the other side of the fraction. So in this case, the denominator, 1 over e to a big number. And so 1 over e to a big number is really 1 over a really big number, which is essentially 0. So that means that this whole thing, e to the negative x, as the x values get larger and larger, this part right here approaches 0. And since I'm multiplying 6 minus 6x cubed times 0, anything times 0 equals 0. So the limit as x approaches infinity of 6 minus 6x cubed times e to the negative x is 0. And then we'll do, I think, one more. So let's look at one more example like this, another e example. This time where x approaches negative infinity. So I'm going to think about approaching negative values, negative big numbers. So I can think of negative e to the negative 1 over a negative big number. And then a negative divided by a negative is a positive. So negative e, negative 1 divided by negative big is 1 over big. And 1 divided by a big number is pretty much 0, like a big, really big number. So this is the same as negative e to the 0. And e to the 0 is the same as 1. Anything to the 0 power is 1. So I have negative 1. And oh, look, that means we get negative 1 as our answer. Okay, so this video will help with the second